So I was talking about thermodynamics of solutions, multi-component solutions. So multi-component solutions means it is basically a mixture of multiple components, and the mixture gives rise to a homogeneous, non-reacting. It's a homogeneous, non-reacting mixture of components where you cannot distinguish one component from the other, and they form a solution. Okay, so that is the solution that we define, and we'll continue with that. Now, as you know, a little bit of reprise. So, if you think of Z, which is an extensive thermodynamic parameter that depends on the extensive thermodynamic parameter, it's a function of Z, can be a function of temperature, pressure, and mole number of different components like component 1, component 2, and component says up to C. And see, N1 is the number of moles of component 1, N2 is the number of moles of component 2, Nc is the number of moles of component C. Then basically you have total number of moles. If you look at total number of moles, N equals to summation, so equal to 1 to N, equal to 1 to C, and I, right? So Zm is nothing but, which is Zm or Zm is a molar thermodynamic property, and molar thermodynamic property means thermodynamic property per mole, right? It is per mole. It's an intensive quantity, so it will be defined as Zm or Zm equal to Z by N. Okay, now let us look at the partial molar property I have already defined, right? In the last two classes I have already defined. So Zk bar, so Zk bar is the partial derivative of Z with respect to Nk, that is with respect to species K, the concentration of species K in terms of mole number. So del Z del Nk, that means I want to look at the change in the extensive property Z if I add or remove some amount of K component, right? One of the components is K component, means the component K. So I am looking at Zk bar means partial molar property of component K in the solution. So remember, when I am talking about partial molar property, I am already considering a mixture or a solution, right? I have considered a mixture. I want to look at the contribution of component K to the extensive property. So Zk bar is defined as the partial derivative of Z, is the property with respect to Nk, which is the mole number of species K or component K, keeping temperature, pressure, and other species mole numbers, that is J are the other species, and J not equal to K. See, J not equal to K, and this is the other species mole numbers are kept constant. So only mole number that I am changing or varying is the mole number of component K, and as a result I want to see the variation in Z, means variation in the extensive parameter. Remember, I am looking at the variation in the extensive parameter, not the variation in the molar parameter, right? I am not looking at the molar thermodynamic property, but I am looking at, so that is the definition of partial molar property. See, remember, partial molar property is always defined with respect to, when I express it in terms of partial derivative, then it is with respect, so the quantity that I am, means basically the quantity, the numerator is basically the extensive thermodynamic property, right? It is the extensive thermodynamic property. So this is the partial derivative of the extensive thermodynamic property with respect to the mole number of component K, keeping temperature, pressure, and mole number of all other components fixed, right? Keeping mole number of all other components fixed, temperature fixed, pressure fixed. We want to see how the extensive property varies as a function of variation in the mole number of component K. Change in mole number of component K. Now, if that is so, Z being an extensive property, right? Z is an extensive property. So at a given temperature and pressure, if I write at a given temperature, say at a given temperature T and at a given pressure P, Z, there is extensive property. This extensive property is a summation of the partial molar properties of the components K, where K can vary from 1 to C, right? So this is a sum of the partial molar properties multiplied with the or weighted with the mole number of each component. So basically this is nothing but, if I expand, Z equal to N1 Z1 bar plus N2 Z2 bar plus so this Zk bar or Z1 bar is the partial molar property associated with component 1 or partial molar contribution of component 1 to the solution. Okay, and this partial molar the partial molar property of component 1 or associated with component 1 in the solution, and the solution has an overall property or an extensive property Z, right? Now if that is so, I have also defined the Gibbs-Duhem relation, right? Gibbs-Duhem relation, which is basically, so I did it for Gibbs free energy, I showed it for molar volume, I showed it for the total volume. So if you look at any extensive property Z, then it is Nk dzk bar equal to 0. So basically Nk dzk bar, again summation from K equal to 1 to C. Okay, so if you have repeated indices, remember that if you have repeated indices, we can also use a Einstein summation convention. So basically this means there is always a sum of the repeated indices, and the repeated index is K, and K denotes the component here. K denotes the component K here. So number of components here is C, and the components are denoted by 1, 2, 3 up to C. Okay. So now if you look at dz, dz is N1 dz1 bar plus N2 dz2 bar, plus also you will have, now this part you have to remember, this is something, you have this one, and you also have Z1 bar dN1 plus Z2 bar, right, dN2 plus ZC bar D and C, right? So you have this term plus you have another term which is K equal to 1 to C. This will be ZK bar D and K. Now according to Gibbs-Duhem, this term Nk dzk bar equal to 0, right? So N1 dz1 bar plus N2 dz2 bar plus Nc dzc bar, all of these are 0. So this term goes to 0, right? So this term goes to 0. So this will be 0 according to Gibbs-Duhem. But what is remaining then is this term, right? And this is the Euler relation. You see Z equals to N1 Z1 bar plus N2 Z2 bar plus Nk Zk bar, or I can write this as summation k equal to 1 to c nk zk bar. See, this is the Euler relation, right? This is Euler equation or Euler relation, right? For example, G equals to H minus Ts plus mu I Ni. Now, if you think of a constant pressure and temperature, then G you can basically write as mu I Ni, right? Mu I Ni, where mu I is the partial molar free energy of component I or chemical potential of component I. As I told you previously, chemical potential of a component basically is nothing but the partial molar free energy of that component in a solution, right? Now, what types of solutions are possible? Solid in liquid, solid in solid, liquid in solid, mixture of gases. So, any type of solution is possible. Now comes an interesting part, okay, which is basically, again, I am reprising, I have already defined it previously, but please listen, because this part is very, very important when you want to understand solutions or thermodynamics of solutions, right? When you want to understand thermodynamics of solutions, you do have to remember the Gibbs-Duhem relation, okay, which is nk dzk bar. So basically what it tells is that this dzk bar means if you have a partial molar property, if you do a differential of that partial molar property and weight it with the mole number, then basically the sum of these will always go to 0. That's the Gibbs-Duhem relation, right? And also as a result, we can tell from this equation, means that this is the equation, this is the Euler equation. From this equation and this equation, we can tell dz is nothing but sum for all components zk bar, that is the partial molar property, times the differential of the mole number, right? The differential of the total differential of the mole number, dnk, right? Now look at this. Say for example, you have these components, like 1, 2 and 3. You are adding them. Once you add them, you get this guy, which is basically a mixture, or if it's a homogeneous mixture, then it becomes a solution. So 1 plus 2 plus 3. So all these components are coming, right? So this is component 1, this is component 2, and this is component 3. Right? Now, if that is so, the property that it had is Z10, and the property here would be Z20, and here it is Z30. Now, if it's a 3-component system, then Z0 in this case equal to Z10 plus Z20 plus Z30. See, this is before mixing. See, these are before mixing. We put them together. So before mixing, the Z0 is basically, now remember, Z10 is basically molar property or property of component K. So Z10 is molar property or property of component 1 per mole before mixing. So this is property of component 1 per mole, or molar property of component 1 before mixing. Before mixing means it is in the component is in the pure state, right? It's a pure component. So basically ZK0 is property of component K per mole before mixing in the pure or in the reference or in the standard state. Okay, when you have a superscript of 0, I am denoting what is called a standard state. Now, if I have this standard state and then the delta Z mix, okay, is equal to, so delta Z mix is basically the change in the molar property or relative change in the property. So you can call it like change in property due to mixing. Change in property due to mixing is delta. So that's why there is a delta sign. So it is change in property due to mixing. So that is equal to Z solution, Z of the solution minus Z0, where Z0 is the sum of the molar properties of pure components weighted by the mole number. Sum of the molar properties of pure components weighted by the mole number. If you sum it up, then what you get is Z0, and Z0 is an extensive property, but that's an extensive property of the mixture when we are not taking into account any mixing. So it is like Z0 is the sum of properties of pure components 1, 2, 3 and so on, and weighted by the mole number of each component, right? So that is Z0. Now Z solution is after mixing. Z solution comes, so this is after mixing all components, and this is before mixing, right? This is before mixing, this is after mixing. Now once you have after mixing minus before mixing, this is the change, right? Change in the property due to mixing. So change in property Z, extensive property Z due to mixing. So change in Z due to mixing is basically the extensive property of the solution, that is after mixing, minus the extensive property of all the pure components weighted by the mole number of each component, because these are the components, these are the boxes that you are mixing, or these are the containers that you are mixing. So one, basically, say for example 1, the number of components is n, the mole number is n1, for 2 it is n2, for 3 it is n3. So n3 of Z03 is coming, n2 of Z02 is coming, n1 of Z01 is coming, and they give us 1, 2 and 3. But however, the atoms of or molecules of 1, 2 and 3 will mix, right? The atoms molecules will mix to form a mixture, and that mixture, if the homogeneous mixture is nothing but the solution. Now this solution will form, and solution will have some property, right, which is Z solution, and this is before mixing. So the difference between them is the change due to mixing, right? Now Z0 equals to this sum, right? Sum of nk zk0, where zk0 is the property, molar property of the pure component k, right? And molar property of pure component k, and nk is the mole number of component k. And Z solution, when I am writing, this also can be expressed as a summation, but the summation is over now, nk times zk bar. Zk bar is the partial molar contribution of component k to the overall property of the solution. Partial molar property of component k, or contribution of component k to the overall molar property of the solution, and it is weighted by again the mole number of that component, right, and summed over all components. So that Z solution is nothing but Z for us, right? That's the Z that you measure for a solution, and Z minus Z0 gives me delta Z. So delta Z mix, as you can see here, is again Zk bar. Zk bar is the partial molar property of component k minus, again this is a partial molar property, and this is the molar property of the pure component k, right? The difference between them is multiplied or weighted by nk, gives me the delta Z mix, or summed over all components, it gives me the delta Z mix or delta Z mix. So if I look at delta Zk bar, that is for each component. So for each component, so here for example I am considering only component k. I can substitute k by 1, 2, 3 and so on. So, or A, B, C and so on. So delta Zk bar is the change, or this is called relative. This is called relative partial molar property of component k. okay, or change in partial molar property of component K due to mixing. So delta Zk bar is basically Zk bar minus Zk0. Again, this is nothing but the pure slab standard. Now, therefore, delta Z mix, E, which is basically sum of this, which is delta Zk bar. So, if you can see here, I am having this guy, delta Zk bar, and instead of this, I am writing this directly as delta Zk bar. So, delta Z mix is delta Zk bar multiplied by Nk and summed over all components. Now, if I want to do an exact differential, if I want to find the differential of that, so d delta Z mix equals to K equal to 1 to C delta Zk bar d and K. Why? Because since Nk d delta Zk bar will be equal to 0 because of, again, gives to him relation. So as you can see, Gibbs-Duhem equation is not only valid for the partial molar property mu, the partial molar property, but also for the relative partial molar property, that is the delta mu, right? It is the relative partial molar property is the difference in the partial molar property after mixing, difference of partial from that before mixing, right? This is the partial molar property before mixing. This is the partial molar property before mixing. This is partial molar property after mixing. The difference between them gives me the relative partial molar property of component K, right? And so basically, if I extend Gibbs-Duhem relation, then I can write Nk d delta Zk bar equal to 0. Now, if it is so, as we know that the molar property Zm equal to Z by N, where N is the total number of moles, right? And dZm is Zi bar dxi. Now, why is dxi? Because dz, so as you see, dz equals to Z1 bar dn1 plus Z2 bar dn2. Now, right? So now I am dividing. So d z by n equal to Z1 bar d n1 by n plus, which is n1 by n is nothing but x1. So this will become, so this becomes the dz by n or dzm is equal to this, right? So this is nothing but Z1 bar dx1, right? So zy bar dxi is dzm, right? So that we know, right? So now it has become xi. Remember, this has become mole fraction, and previously it was mole number. Mole number is an extensive property, but mole fraction, which is the ratio of Ni and N, right? N is the total mole number, total number of moles of all components in the mixture on the solution, and Ni is the mole number of component I. So xi is a ratio of these, and so xi is an intensive property. And we also know Gibbs-Duhem, for example, was n d mu. So Ni d mu I equal to 0. So we had Ni d mu I summation over I equal to 1 to C equal to 0. Now, if I again divide by n, right, we will get xi d mu I equal to 0, or xi d, let me call it here, dzi bar. So xi dz bar equal to 0 is the Gibbs-Duhem equation, but using mole fraction, right? So we are looking at mole fraction. So this is again a Gibbs-Duhem equation. This is Gibbs-Duhem equation, but uses mole fraction instead of mole number, right? So, and again, Zm can be written as Zk bar. So you have N1 Z1 bar plus N2 Z2 bar plus so on. And if I divide by N again, so if I divide, so Z equals to this, right? Z equals to N1 Z1 bar N1 plus Z2 bar. So if I take binary, say N2, now N1 plus N2 to N. So Zm, which is equal to Z by N, equal to Z1 bar. See, it's already partial molar property, right? It's partial molar per mole, right? And this will be N1 by N, which is basically X plus this will be Z2 bar, right? These are very important relations, okay? When we talk about molar free energy, right? We have already shown it in the tangent construction. I am just reprising so that you are clear with all these important concepts, okay? Now, as you can see that if we do it for the change in the molar free energy, right? We looked at our molar property. We looked at change in property, right? Due to mixing. Change in the total property or change in the extensive property mixing is given by d delta z. So delta z, sorry, just given by delta z. So delta z is the change in the extensive property okay, due to mixing. So therefore, just taking that Q, we can also write something called delta Zm, which is change in molar property due to mixing. Okay, so if you do that, then the Gibbs-Duhem relation, you can see here d delta Zm mix equals to k equal to 1 to c delta zk bar dxk. Instead of writing dnk that we wrote previously, now you can use dxk, right? And dxk basically means it is the differential of the mole fraction of the composition of component k in terms of mole fraction. So delta Zm mix, for example, is delta zk bar xk, right? And therefore Gibbs-Duhem also we can write as xk times d delta zk bar, which is equal to 0. So n1 d mu1 equal to 0, n1 d mu1 plus n2 d mu2 equal to 0 is equivalent to x1 d mu1 plus x2 d mu2 equal to 0. Okay, so delta Zm mix, if I call it as delta Zm, I just denote it as delta Zm for convenience, otherwise you have to always put a comma and all. So basically, if that is so this is the overall, right? Now, but for each of these, what about delta Z1 bar? The delta Z1 bar is the relative partial molar property of component 1, which is again d delta Z dn1, and keeping T, P and Nk, which is not equal to one constant. So delta Z1 bar can be written as, so now you can see you have already done this, okay, this can be written as delta Zm plus 1 minus xm 1 minus x1 d delta Zm dx1, right? How does it work? You please refer to the last week's class and then you can easily find it. It's very important. Otherwise, you can also do this way like this, and delta Z you can write this way like delta Z equals to n delta Zm, and then you can carry out the partial derivative where you will use a chain rule, then basically what you will get, and this is something that I have shown in the previous class, is this plus this. Right? So delta Zm plus 1 minus x1 d delta Zm dx1. Now if you look at this, delta Z2 bar also can be written as delta Zm plus 1 minus x2 d delta Zm dx2. Right? So if that is so, you can see that d delta Zm dx2 is equal to minus d delta Zm dx1. Right? Why? Because x1 plus x2 equals to 1, so dx2 equals to minus dx1. Right? So d delta Zm dx1 or d delta Zm dx2, d delta Zm dx2 equal to minus d delta Zm dx1. Another important thing that I want to mention is that all the partial molar properties can also be written using the same definitions of thermodynamic potentials that we have derived previously, right? So basically, this is the partial molar enthalpy. So if you look at the partial molar enthalpy of component K, which is equal to the partial molar internal energy of component K plus P times partial molar volume of component K. Similarly, the Helmholtz free energy Fk, right? The partial molar Helmholtz free energy of component K equals to partial molar internal energy of component K minus T times partial molar entropy of component K. Similarly, we can write Gk bar, which is nothing but mu K, which is the chemical potential of component K, which is equal to Hk bar. Again, Hk bar is the partial molar enthalpy of component K, and Sk bar is partial molar entropy of component K. Right? And we can also write something like Maxwell's relations for these partial molar quantities. All of these are valid. So this is one Maxwell relation, right, which is basically minus del Sk bar del P, right, del Sk bar del P equals to del Vk bar del T at fixed pressure and mole number. If the mole numbers are fixed and pressure is fixed, and here it is temperature and mole number, so del Sk del P minus del Sk bar del P equals to del Vk bar del T. This comes from the equality of the second derivatives. Okay, so one thing you have to understand is that we define something called activity. Instead of the mole fraction of components in the solution, we define something called activity of component K in the solution. Okay, and we generally never determine the chemical potential of components in a solution. We generally determine something called activity. So activity of components in a solution somehow should be related to the chemical potential, but remember, this is what we determine. Experimentally, we determine activity, we do not determine chemical potential. Now look at this relation. Mu K minus mu K0 equals delta mu K equals to RT ln AK. Okay, this is the definition of activity. You might have recognized this equation. This equation was written as mu K equal to mu K0 minus right. So it was previously now it is instead of xk, so here I have given xk. Mu k equals to mu k0. Mu k0 is the chemical potential of component K in the pure form or in the standard form, plus R times R is the universal gas constant times T times logarithm of ln of xk, right? So something like this, right? Instead of xk, we will now use something called ak, because we can directly determine activity, but we cannot directly determine chemical potential, right? Chemical potential is basically partial molar free energy, and as with different types of energies that we have experienced, energies cannot be evaluated directly, but activity can be determined. Okay, so activity of component K in the solution is nothing but the apparent concentration. Apparent concentration. So as I told you, activity is basically related to the composition of the component in a solution. So activity, if you look at the definition, AK equals to gamma K xk is basically this gamma K term, which is an activity coefficient that comes in, and this xk is nothing but the actual composition of component K in the solution. So as you can see, for different gamma K's other than 1, AK is related to xk, but AK gives the apparent concentration. AK gives the, so basically what I want to say is that AK gives the apparent, it's a measure of apparent concentration of component K. In the solution. Okay, and AK equals to gamma K times xk. Okay, and gamma K is again written as activity coefficient of component K. When gamma K equal to 1, as I told you, when gamma K equal to 1, AK and xk are same, right? Gamma K equal to 1 basically means AK equal to xk, and activity of component K is concentration, is basically the apparent. So remember to use the word apparent. Concentration of component K in the solution, that is AK. Now as you know, AK equals to gamma K xk, and mu K I can write as mu K 0 plus RT ln AK, and that is basically nothing but mu K 0 plus RT ln gamma K xk. Now if gamma K is greater than 1, obviously if gamma K is greater than 1, then this can be written as, by the way, this can be written as mu K 0 plus RT ln xk plus RT ln gamma K. Now this is the part you can see that comes as excess. So now this part, if gamma K for example is greater than 1, this part will be positive, right? If gamma K is greater than 1, so this part is positive. Activity, which is xk times gamma K, activity becomes greater than the mole fraction of component K, and component K behaves as if the concentration of its concentration is more than its actual concentration xk. So as if its concentration is more than its actual concentration, which is nothing but xk. So that's how we define activity of a component in a solution. Similarly, if gamma K is less than 1, then RT ln gamma K is going to be negative, right? If gamma K is less than 1. So AK becomes less than xk, and in that case, the apparent concentration of component K is less than its actual concentration, right? So now we can also look at the mixture of pure components, various pure components, and that mixture of pure components means you have just put them together, you have just added them together, they are not yet mixing, right? They have just been added together, and these are like pure components from 1 to n. Say for example, from 1 to n you have n pure components, or you can think of, instead of making any confusion, you can tell up to x c. So x1 mu1 0, x2 mu2 0, and you have this term. So mu 0 basically is what I am trying to say. So this is xc and this is mu c0, at a constant temperature and pressure. Okay, so let me just use the same color. So this becomes Xc mu C0 at the same temperature and pressure, right? So this is the mixture of pure components. So this is the mixture of pure components up to Xc. Okay, where mu I0 or mu K0 is the chemical potential of pure component I in at temperature and pressure, and that is nothing but the reference, or you can think of like a pure, it's like the partial molar Gibbs free energy of partial molar Gibbs free energy of component 1 in the pure form, which is nothing but the molar, of component 1, right? So now if you look at condensed mixture, that is condensed mixture means mixture of liquids or mixture of solids. In general, for mixture of liquids or mixture of solids, we consider the PV work, and we have already seen some examples. The PV work is negligible. So basically we keep P equals to 1 bar or 1 atmosphere only when the P is of the order of some few kilobars or some like 10 gigapascals or more, that we have also shown. You will see that in such cases PV work becomes important for the condensed mixture. So if it's a condensed mixture of pure components, so basically you have a mixture of pure components, say for example copper and nickel, you have mixed together and you have formed a solution, a solid solution, or you have taken say some acetone and water and you have formed a solution, or some ethanol and water and you form the solution. So in such a case, the pressure is assumed to be 1 bar or 1 atmosphere until very high pressure is applied. This is because in such a case the PV work will be really negligible, right? If it's a solid liquid solid type of, or liquid type of mixture, so in that case you have to remember that we have to keep pressure fixed at 1 bar or 1 atmosphere, and we have to basically, once you keep pressure fixed, you can define properties, molar properties or partial molar properties of a the components in terms of only temperature, because pressure is fixed, right? For condensed mixture we are taking the pressure fixed. So basically, as you see, that you can express the molar free energy in terms of partial molar free energies or chemical potentials. Again, here we are telling, by if I take a binary mixture and before mixing, this is before mixing, has started, because the mixing process is what? You have collection of A atoms, which is basically your species A, and you have collection of B atoms, your species B. You put them together. Unless they mix, they are still in their pure form. The blocks are in their pure form, right? They have to mix, and once they mix, then basically you have formed a solution. Before that, it is like you have placed one block of A atoms, one block of B atoms, okay, and so on. So basically, if you look at the molar free energy as a function of temperature, and so again, pressure is fixed. Remember, for one phases, because pressure does not do much, okay, the PV work is negligible. Okay, so basically Gm is a function, is equals to, so Gm is basically nothing but mu 0, and mu 0 is nothing but the partial molar Gibbs free energy or chemical potential in the standard state, which is equals to Xa mu is 0 plus Xb mu v 0, right? Xa mu is 0 plus Xb mu v 0. Now, as you can see here, you have this mu is 0, you have this mu b 0. There is nothing much has changed. So this point is mu is 0 and this point is mu is 0. Okay, so in the next class, I'll start from here and I'll tell how activity modifies the property of the solution. Okay, how this definition or how all this that you have learned, basically why this before mixing and after mixing, although I have given a small atomistic picture before mixing and after mixing, how does this properties get modified is what I'll do in the next lecture. Thanks so much.